Okay, chapter 6, section 3. We are going to be discussing trends found on the periodic table. Okay, I'm going to skip this part. Here are our objectives for all of chapter 6, section 3. At the end of this section, you should be able to state the period and the group trend for atomic radius, ionization energy, ionic radius, electronegativity, and electron affinity. Our focus today is going to be on atomic radius, and we may get into ionization energy. We'll just have to see. We are definitely going to describe the formation of ions today, so you're going to want to make sure you can do that at the end of today's lesson. And then we're going to practice sequencing elements in order of their periodic trend. All right. So basically, if we think about what the definition of a trend is something that can be predicted. Fashion trends, stock market trends, things that can be predicted, or with some accuracy anyway. I predicted that we wouldn't be at school today. I was very wrong.
You're half wrong.
I'm half wrong. Thank you, Patrick. That Yes. But like I said, a trend is just something we can predict. The periodic table is actually not just a list of the elements on the table. It's a tool that we can use to identify things about the different elements there, because it's full of trends, and these are stuff that occur periodically. That's why it's called a periodic table of elements. That's where it comes from. We can look at the trends of the periods and the groups, and we can predict things about the different elements. Like I know that if I'm looking at the bottom left corner, those are going to be highly reactive metals. And if I look at the far right last group, those are going to be non-reactive gases. Those things I can predict just based on their location on the periodic table. Okay. The very first trend in our first part of our objective today is I want you to be able to define atomic radius, and I want you to state its period trends and its group trends. So our first one is atomic radius or atomic radii. One is just the plural version. They mean exactly the same thing. So atomic radius, atomic radii, those words are just referring to the same thing, just one is plural. The definition, and you need to know this is one of those facts that you have to put into your mind to do well on the assessment portion and to be able to do the application parts of this. Atomic radius is defined as 1/2 of the distance between two nuclei of bonded identical atoms. The reason that we have to measure the radius of an atom like this is because if we were going to measure the radius of a basketball, I would just measure from the center part of the basketball to the very outside part. And I know where that is because the basketball ends. It's a solid piece. Atoms aren't like that. Atoms are more like a cloud. We call that actually the electron cloud. There's not a defined edge, the edges are blurry. And so, since I can't tell you exactly where the electron cloud ends, I have to figure out a way that I can measure the radius accurately. And the best way to do that is to look at two atoms that are beside each other. They're bonded, they're identical, and measure the distance between the nuclei, which is what I'm doing right here. This is between one nucleus and the other nucleus. And if I take and divide that in half, I have my atomic radius. All right, so atomic radius, one half the distance between the nuclei. The trend, so our next objective is to be able to state the period in the group trend. As we read from left to right across the periodic table, atomic radius is going to decrease. And then we read the periodic table just like we read the page of a book. We read from left to right and top to bottom. So if we look at the numbers, the values, like on a chart, we would notice that they would get smaller as we go across. The reason for this, we can kind of look at in this diagram that I've got here. If we were to look at three elements that are in period 4, so all of these are in the same period. I have potassium that is on the far left of the periodic table. Iron is about in the middle, and then bromine is on the far right side of the table. I can see that the nucleus gets larger as I go across, and let's think about why that is. The atomic number of potassium is 19. Atomic number of iron is 26. The atomic number of bromine is 35. The nucleus is getting bigger because that's where the protons and the neutrons are. So the more of those I have, the bigger my nucleus is going to be. If we get bigger, though, and the electron cloud stays the same, you'll notice that the distance decreases. So our electron cloud is going to remain the same size, but our nucleus is going to grow. We're getting more protons and neutrons. The nucleus gets bigger, so the distance is going to get smaller. All right, so we're going to decrease as we move from left to right. If we look at our groups, though, our groups are the vertical columns. We're going to notice that it's going to increase as I go from top to bottom. The reason for that can be observed if we look at some elements, just some quick diagrams of some elements that are in the same group. So if we look at some group 1 elements like lithium, we go about halfway down the group and we get rubidium, and then all the way to the bottom of the group we have francium. Absolutely, the nucleus is getting larger, but every time we add a proton, we have to add an electron. Lithium only has 3 electrons, so its electron cloud is pretty small. Francium, on the other 7, has to have 87 protons and 87 electrons. So its cloud is much, much larger. And so you can see that the distance between the nuclei is getting larger because the electron cloud has to be larger. So the nucleus does grow. You're not seeing that wrong. But because the electron shells have to get bigger, the distance is going to increase, making our atomic radius larger. All right. So trend number 1 is atomic radius. 1/2 the distance between 2 bonded nuclei or atoms and their nuclei. We look at the distance between the nuclei. The period trend is it's going to decrease across the period and it's going to increase down the group. Those are facts that you need to know. You need to think about those. You need to put them in your memory and you need to be able to work with them because you're going to have to know the fact part in order for us to do the sequencing part. You have to know that it increases from left to right and decreases from top to bottom. I'm sorry, decreases from left to right and increases from top to bottom. And we're going to come back. We'll do the graphing exercise later. All right. So first objective is first part of the first objective is done. The next objective is about ions. Before we can talk about things like ionization energy and electron affinity and electronegativity, we need to understand what an ion is. Ions exist because every atom wants to be its most stable self. And in order to gain that stability, they will gain or lose electrons. They will gain and lose electrons because they are trying to form an octet, okay? The noble gases are group 18 elements, and each of those noble gases has 8 valence electrons. These are their outermost energy level. And because it has those 8 electrons, it has achieved stability. Noble gases rarely, if ever, react. Like they have to be forced into it. And there's only like 2 instances where you even get a compound with a noble gas. They are great by themselves. They are completely stable in where they want to be. So all the rest of the elements on the periodic table are trying to get that same noble gas configuration. If they have 8 electrons in their outer shell, then they're probably going to be exactly the same stability as the noble gases are. And so that's what it does. If it's going to gain and it's going to lose in order to get 8 electrons in the outer shell. When it does this, it creates an ion. An ion is defined as an atom or group of atoms that have either a positive or a negative charge.
Kenneth Griffin, come to the front office.
Okay, so ions are created because elements want to be stable. And they are stable when they have 8 electrons in their outer shell. Not 8 electrons total. We're only talking about the ones on the very edge. The last level, the last shell needs to have 8. Okay. I'm sorry. Courtney, did you have that? I didn't. Okay. Just wanted to. Saw you writing. You're going to get 2 kinds of ions. You're going to get cations, and I promise it's not a cation. I do have people sometimes want to tell me that. It is pronounced correctly as a cation. Cations are the positive ones, and they form when we lose electrons. If electrons are negative and I lose some negative charges, I become positive. That's right. So cations are going to have a positive charge, and that happens because they're losing those negative electrons. The metals on the periodic table are what form cations. And if you remember back from our section 1 discussion, about 85% of the elements on the periodic table are metals. So that also means about 85% of the elements on the periodic table are going to make a positive ion, a cation. So they're going to lose electrons and they're going to make cations. Right. You do not have to write this next sentence. I'm just telling you how we're going. We're going to do some examples here and look at how cations are formed. And we're going to look at it with electron configuration and Bohr models. So let's look at our first example here. Let's look at sodium. Sodium is a metal. It's number 11. It's in group 1. If you've started your Google slide project, that's the alkali metals. A neutral atom of sodium has 11 protons and 11 electrons. It has an equal number of positives and negatives. So it has 11 electrons and 11 protons. If we look here, though, if we look at how this works, if we draw a Bohr model, we have 2 in our first one, 8 in the next one, and then we have this 1 electron on the outside. The outermost energy level is where the electrons are either going to be lost or gained at. Right now, sodium has 1 valence electron, 1 outer electron here. It's got 1. Is that 8? No. So we have to look at it, and nature follows the path of least resistance. What's going to be easiest? What's going to take the least amount of energy? So So sodium's going to have a choice here. It could go out and gain 7 more electrons, but it's going to have to spend the energy to get 7 more electrons, or it could just lose this one. If it loses that electron, this is what it looks like. So it's not going to gain 7. It's going to lose 1. That's easier. And when it does that, we only have 10 electrons. So I went from having 11 protons and 11 electrons to now I have 11 protons and 10 electrons. So overall, it's positive. And it makes a stable ion. Does that make sense? Okay. A good way to remember this is cations are positive. Of course, I do love a good pun. Puns make me happy. They really do. So cations are positive. And that really sticks with people. I literally have students from 20 years ago that'll be like, cations are positive when they see me in Walmart and stuff. And I'm like, I'm glad I made an impact. All right, so if cations are positive, then guess what anions are? Negative. That's exactly right. So our first type of ion was the cation, and our second type of ion is the anion. Anions are negative. Cations are formed when we lose electrons. Anions are the opposite of that. They're formed when we gain them. Metals form cations. Well, the non-metals form anions. All right, and once again, we can look at our Bohr models, and this becomes obvious to us of which path fluorine takes in order to achieve stability. If we look at fluorine, well, any anion, but fluorine's a good one to look at. A neutral atom of fluorine has 9 protons and 9 electrons. If having 9 electrons, though, when we fill in our Bohr model, we notice that we only have 1, 2, 3, 4, 5, 6, 7 in the outer circle. 7 doesn't even, that's not going to work. 8 is great. 7 doesn't even rhyme with great. 8 is great. 7 heaven? But no, 8 is great. That's what we're sticking with. So we have this empty spot here. Now, fluorine has a choice. He could go ahead and just ditch all 7 of his electrons in the outer shell and be like the noble gas helium. Or he could do the easiest thing would be to gain 1 more. When he does that, we now have more negative charges than we have positives. We have 10 electrons instead of 9. So we have 10 electrons, which are negative, and only 9 protons, which are positive. But either way, this makes this stable. Look at it. Yay. And that's ions. So ions are charged atoms or groups of atoms. They are formed when we lose or gain electrons. And you need to be able to identify which is which. Cations are positive. All right. Are there any questions? Awesome. All right. Well, this is where we stop for today.